transport. So by carrier we mean electrons and holes. These are the carriers in the semiconductor material. So when we talk about transport, their movement, electrons and holes, how they move or what causes them to move inside the material. Okay, so that is our consideration. So the first way it can move is under the influence of an electric field. So number one, we will look at what is called as drift current. Okay, so the moment you hear a drift current, immediately what should come into your mind is the cause for drift current is electric field. Electric field is the cause. There are other ways in which carriers can be transported, and these carriers are charge carriers. Electrons have negative charge, holes have positive charge. So when they move, they result in current because they have charges associated with them. So how do for example electron move in response to electric field? We know the electrostatic force acting on a charge Q. Okay, the electrostatic force on charge Q is Q into electric field. Okay, so in general electric field is a vector, so we will assume that it is in a particular direction, and we are looking at the magnitude. E is the magnitude of the electric field in the direction of the field. Okay, so if Q is the charge, then the electrostatic force acting on that charge is Q into E. Okay, now the dimension of charge is Coulomb, and electric field, so where E is the electric field, and the unit is unit that we will use in this course is volt per centimeter. Okay, SI unit is volt per meter, but for semiconductor physics and electronic devices we will use volt per centimeter. That is more convenient. So this is the force acting on, this is the electrostatic force acting on it, and whenever there is a force acting on it, if you consider Newton's law, this force will try to accelerate the electron. Okay, but there is a difference. Electrons are not free particle. Okay, they are inside the crystal. We are considering electrons inside the crystal. So the mass of the electron is not the rest mass, it is basically the effective mass that effectively you can treat electron is moving with a moving freely with a different mass. So the picture, that is a picture that we have developed earlier. Okay, from the energy band structure, we compared the energy band structure of electrons in the crystal with the free electron energy band structure, and both have a similar parabolic approximation at the bottom of the conduction band and as well as at the top of the valence band. So because of this similarity, we have assigned an effective mass to the electron, which depends on the curvature of the energy band structure, and so those values for effective mass comes out of the energy band structure which we have derived earlier. So we will now use those concepts while applying this to the semiconductor material. So when this force acts upon the electron, this force will try to accelerate. So from Newton's law, this is Newton's second law, F is equal to, if there is a force acting on a body with some mass, but now we are taking effective mass, not the rest mass. So if you take it for electron, then we can give E as a suffix, or even you can give N as a suffix, N for negatively charged carrier, and P for positively charged carrier. One of this notation we can use. So I think we have earlier used M star E, so I will stick with that. So M star E into the acceleration. So this force is coming from the electrostatic force. Therefore, M star E is equal to Q into E. Now, acceleration is the rate of change of velocity. So you can write this as d v of electron. Okay, so this velocity is also called as the drift velocity. So I will use another subscript to say that this is not the normal velocity, but it is the drift velocity. So this divided by dt is equal to Q into E. Now if you take this charge Q, so Q I will define like this: Q is equal to minus modulus of Q for electrons, and it is modulus of Q, to avoid confusion, for holes. Okay. Now that is M star E, or let me take M star E to the other side. So dVe, the drift velocity, is equal to Q by M E star dt. Okay, I can write like this. And now if I integrate this on both sides, integrating on both sides, we get VE, drift. Okay, so drift velocity, you will get it as a function of time, Q by M E star into T. Okay, so I integrate from 0 to T, okay, which is a definite integral, and so we assume that T is the time then force is applied, and as a result electrons start accelerating, and its velocity is proportional to time. Now in this picture it looks like the electron is going to continue to increase its velocity and keep on increasing its velocity, and if that is the case, then it can even cross the velocity of light. Okay, but actual picture doesn't allow a continual increase of velocity. Now this you can why it can't increase why it can't increase the velocity continuously. So what is the reason for that? The reason is same as when you drive a bike or a car and you give accelerator, then you give an like you burn the engine, and then try to give a constant amount of combustion, then you are basically applying a force on the vehicle. A force is acting on the vehicle, which is making it to move. But even if you apply a constant force, it doesn't mean that the vehicle is going to continue to increase its speed. It will continue to increase its speed until it reaches the maximum speed. And once it reaches maximum speed, though there is a force acting on it because of the engine is working, but still its velocity doesn't continue to increase. The reason for that is there is an opposing force by the air, okay, which is you can call it as the drag force or the damping force of the air, and as a result your velocity reaches a maximum value and then it stops increasing. Same thing happens with the electron also. Okay, when the electron, though there is a constant force acting on it, which is Q into E, but it can't continue to increase its velocity because there is going to be an opposing force. And what is the opposing force here? The opposing force that acts or that limits the speed or that limits the velocity from increasing is the collision, is the scattering or collision, scattering mechanisms. And there are particularly two kinds of scattering mechanisms that will take place inside the semiconductor. So which are of two types. Okay, so number one, we call it the collision from the vibrating lattice. Okay, the collision with the vibrating lattice. I hope everybody remember what is a lattice. We started in the first part of the course with the lattice. So there is a 3D lattice. We said that they are corresponding to the atoms sitting at a regular interval. If you're taking a silicon, we saw that it has what is called as a diamond structure. So atoms are placed in regular intervals in a particular way. At zero temperature they don't move, but that is only at zero temperature. But any object which we use for making devices, they are at high temperature in the sense compared to zero. For example, at room temperature to start with, maybe 300 degree Kelvin. So all these atoms are not going to sit idle there. They are going to jiggle about their mean position. So this is what we call as vibrating lattice. It is also technically called as phonon vibration. Okay, phonons are basically a quantum mechanical way of looking at so they are treated as particles corresponding to this vibration of lattice. Okay, so we will not go into those details, but just understand that these lattice points are not going to sit idle. If they are sitting idle, electron will not have any trouble. It will not face any scattering. Okay, because electrons are not just particles like balls. They are quantum particles which has wave nature, and therefore they can just move through the entire lattice without any trouble, provided the lattice are not vibrating. But that is a very ideal picture. In principle or in practice, these lattice are going to vibrate. All the atoms in the lattice are going to vibrate in their mean position, and there are different kinds of vibrations, and so they are further classified into optical phonons and acoustic phonons, etc. But we don't need all of that for our present discussion. But these vibrations are non-ideal aspects of the semiconductor, which we have not incorporated in the earlier derivations. Okay, and therefore they will obstruct the motion of electrons or charge carriers inside the semiconductor. So this is one mechanism. Secondly, the other type of non-idealities that we talked about earlier is the collision with ionized impurities. Of course, we are purifying silicon to very high, very high, purity levels, but something like 1 in parts per billion. Okay, for every billion silicon atoms, we try to achieve purity where 1 in 10 raised to 9 silicon atom will be an impurity atom. But then we purposely add impurities, which is due to doping. Okay, in order to tune the properties of semiconductor. And in the earlier classes we have seen how to calculate the number of carriers, that is electrons in the conduction band, when after we dope the pure semiconductor with impurity atoms such as arsenic or phosphorus from the 5th group, or gallium, aluminum, etc. from the 3rd group. Okay, you can have compensated doping also, where elements from the 3rd group as well as elements from the 5th group both are put into the intrinsic semiconductor. So all of these impurities which are added, if they are ionized, so they are scattering points. Okay, they are basically interfering with the motion of electron. So they will not let the electrons to continue to increase its speed, because after it reaches those impurity centers, they will be scattered off. So their direction may be reversed. The particle will come back. So these are the two mechanisms. So one is due to the phonons, the other is due to ionized impurities. Okay, the ionized impurities have a Coulombic potential associated with it. Okay, once for example a donor atom gives away its electron, so there is a net positive charge it acquires, and this potential become visible to the electron when they move near to it, and they get scattered off. Okay, they get attracted by that potential. Or if it is a acceptor impurity atom which has accepted a net electron, a fourth electron, which will have a net negative charge, and that will try to repel the electron or attract a hole. So all of these mechanisms are there, just like as I said about the vehicle which is being applied by an external force. As the speed increases, the drag force also increases. Okay, and thus the point at which these forces become equals, the velocity gets saturated. Similarly, the velocity of the charge carriers, electron or holes, they will get saturated. So due to these mechanisms of scattering, what happens, we can model that these electrons or carriers, the carriers get obstructed, and their energies which they have acquired by speeding up, their kinetic energy. Okay, so here by energy I mean kinetic energy gets lost. So then it is as if they have to start all of a sudden again from that point of time, from zero. So again the acceleration will happen, and by the time it reaches some maximum speed, again another scattering will happen. So this is a random process, statistical process. So we have to talk about an average velocity. So the formula that we have done is Q by me star into T. So if I take the average velocity, it turns out, therefore, the average velocity means we are not focusing on just one electron. Each individual electron, if you focus, they may reach different velocities before they getting scattered. But if you average out by using a statistical model, then we can talk about an average velocity of the carrier, okay, of the electron that we are looking at. We can talk about the same thing with respect to holes also. So now average I will write like this: velocity of electron, which is drift velocity. So this average velocity, individually they may be different, but on the average you will get it as so what was it? Yeah, Q by m star Q by m star, and I will write it as tau here. I will explain what is this tau. Okay, so there is also one T which I missed here. So this will be multiplied with T. So this into T into electric field. This into electric field. Okay. So so now I have to tell what is tau. So tau is also a statistical parameter. It's basically referring to time. In place of t I put tau, where tau is called the mean free time between collisions. Okay, some may collide at a time larger than tau, okay, and some of the electron or carriers may collide at a time lesser than tau. But what is the mean value? That is what is going to determine your average velocity. So if it is electron, we can put again a subscript here, tau e. So tau e is the mean free time between collisions for electrons. Okay, for electrons. Now this also, tau also depends upon various parameters relating to the crystal also, like what is the density of electron, etc. So right now we just got a expression for the average velocity now, and that expression, if you look at, that is proportional to the electric field. So therefore we see that the average velocity is proportional to the E field. Now this bracket thing, whatever is in this bracket, it looks like a constant, because if you look at the electrons in the bottom of the conduction band, they have a constant curvature after the parabolic approximation that we have studied earlier. So m star is basically a constant, and tau is basically a constant, which is the mean. Okay, it is a constant provided the temperature is fixed, as well as the impurity concentration is fixed. Okay, so I have to add that note. So tau is called the mean free time between collision for electrons, and it is a constant provided temperature and impurity concentration remains constant. Okay, So because it depends on the temperature and the impurity concentration. So I told you about two mechanisms. One is basically lattice vibration, and lattice vibration definitely depends on temperature. So if there are more vibration, it is there's a great chance that you will get collision in a short interval of time. Tau will be smaller for higher temperature, whereas if you look at the impurity, the scattering from the impurity, so if the impurity concentration goes up, that means if you dope in larger amounts, then also it is going to remain constant. Okay, so now this quantity, so we see that the average velocity is proportional to electric field, and Q into tau E divided by me star, we will define it as what is called as the mobility. Okay, mobility, mu suffix E, mobility of the electron. So as I told you, tau depends so much, it depends so much on temperature and impurity concentration, etc. And later we will see that it is also going to depend on the electric field itself. Okay, so that is another effect which we will come, especially at large value of electric field. There is going to be dependence on electric field also. But right now we are considering, let's say, low fields. That means the applied electric field is relatively less. Low field means, so let me say for E less than say 30 kilovolts per centimeter. Okay, this is pretty high. So normal applied voltage will create an electric field which are normally less, but it also depends upon various other factors how much is going to be the electric field, because electric field basically depends on not only on the potential but also on the distance across which you apply the potential. Okay, so E is V by D, right? So if D reduces, say, even if V is just 5 volt, but if D reduces to very smaller value, then also it can generate very high electric field, which is in fact what happens in a Zener diode. So Zener diode breakdown happens exactly because of the reason we create very high electric field with the low values of potential. So we need to look internally what is actually the reason for that creation of high field at 5 volt, or yesterday we saw 7.5 volt in the experiment. We had a breakdown. So the reason for that is like D across which the potential is applied, reverse bias potential is applied, is very, very small. And how to create that much small region across which the potential is dropped? So there are various mechanisms like doping it to a very high level. So most of the Zener diodes are very heavily doped with impurities. Okay, so that D, that is the distance between the p-type and the n-type material, or the depletion region width, becomes very, very small. But we will come at it at a later part of the course. Alright, so if these electric fields are much lesser, then this expression, this is the expression for mobility. And similarly, we can talk about mobility of holes. We can find the mobility for holes. I took electrons, now we can take holes also. So only difference is that Q is the only Q is going to be positive. For electron, Q is negative. So thus mu E, I can write it as, if I put modulus and a minus sign here, then tau E by m star. So this is for electrons. So this is for electrons. Then mu for holes. So let me put H here, mobility for holes, and that is going to be modulus Q tau H divided by effective mass. So here we are talking about the mass of the holes, which we showed earlier that it is going to be positive mh star, because we are taking the top of the valence band. Okay, from there we get mh to be positive with a positive charge. Okay, positive mass with positive charge for holes. So these are the mobilities. So if you have the mobilities, we have the velocity. Okay, it is just the product of mobility with electric field. Okay, again I am emphasizing that this is valid only for low fields. Okay, okay. So I have to say that the expressions is valid only for low fields, low electric fields. Okay, again E less than 30 kilo volts per centimeter. Okay, what will happen after we increase the electric field beyond that? That I will come later. So this is mobility. Now if electron is moving with a velocity v, then how much is the current? So now we would like to calculate the current. So before we move on to current, the quantity that I would like to calculate is current density. So calculation of current density. Okay. Ultimately we have to bring everything in terms of voltages and currents. Okay, so that is how we are proceeding gradually from all the semiconductor details. We need to come up to what we can measure outside, what we did yesterday, the characteristics. Okay, how those things are going to be determined. So current density, what is current density? Current density is usually denoted by a symbol J, capital J. And if you are talking about electron current density, then we can put some subscript, say E or N, and then for holes we can put H or P. So conventionally we use Jn for electrons, Jn, and Jp for holes. So you can remember N stands for electron, P stands for holes. It is referring to their charges. Okay, so and again by here we are still continuing our discussion with the drift. So in order to distinguish it from other mechanism, which we will come later, so I will put DRF just to specify that we are talking about a drift current density. Okay, calculation of drift current density. Now J, J in general, J is basically I divided by A, where I is basically the current that we talk about, and A is basically the area of cross section. Okay, current divided by area of cross section is what is called as the current density. Okay, or current per unit area. It means we are talking about current per unit area. But mostly we will have equations in the study of semiconductor devices. We will have equations mostly based on current density. Okay. Now current density is a convenient way of talking about current, and for example, if you put Ohm's law, everybody knows that you can write it as V is equal to some constant R into I. The same Ohm's law you can write in terms of current density as, instead of voltage we write electric field, and here we will write rho instead of R, that is resistance is replaced with resistivity, and then and then instead of current we will have J. Okay, so these are like analogous way. So you can say that this is integral form. We are considering the entire device when we talk about a resistance, but this is differential form of Ohm's law. Okay, so derivation becomes more convenient with the differential form, but anytime we can convert back into integral form by integrating over the entire dimension, the geometry of the device. Alright, so J is current density, and we would like to find out what is J. So let us consider a picture of motion of carriers. So you have say a lot of electrons which are moving like this. So they are all moving in this direction, say, and the material in which they move has some cross section like this, which is what we call as A. Okay, A is the area of cross section, and the electron is moving, and a little while ago we have found out what is the speed or the velocity with which they move. The drift velocity we have found out. Suppose the drift velocity, so V d E, that is what we said. So electrons are moving, so definitely the electric field is in this direction. Okay, this is the direction of electric field for electron to move in, because electrons have negative charge, so they will move in the opposite direction. Now if you find out what is the current density, first of all we need to find out how many number of electrons are crossing this cross section. So this area is considered perpendicular to the motion of electrons. So how many electrons? The question is how many electrons cross the area A in unit time. So what is the number of electrons that cross the area, the cross sectional area in unit time? Okay, so cross sectional area is given as A, so the number is definitely proportional to A. What else the number depends upon? So how much time or how much distance the electron move in unit time. So the distance traveled by electrons in unit time is nothing but its drift velocity, which we denoted as this V d E. Okay, so velocity by definition means it is a distance traveled divided by time. So the distance traveled by electron in unit time is the velocity. Okay, so all those electrons, if you consider unit time, how much electrons are crossing, all those electrons in this volume, which is it is like a cylinder with height equal to the drift velocity, height equal to drift velocity. So if the drift velocity is this much is the drift velocity. So this distance cylinder, and all the electron inside the cylinder, okay, they are going to come out through the cross section. Now how many electrons are there in the cylinder? Therefore let me make that statement. All the electrons electrons inside the cylinder with the cross section area A and let me say length, since the cylinder is in x direction, and length VED will cross the section in unit time. Okay, so we are almost near to understanding the value of current or current density. So how much electrons are there? Okay, so if in that given volume, in this volume, we have n is basically the density of electrons, n into then the volume is VED into A. Okay, so this is the volume and this is the concentration of electrons. Okay, so concentration of the electron multiplied by the volume, so that will give you the number. So this is the number of electrons, okay, and which is moving in unit time through that cross section that we have considered. Now what we want is so we need first of all to calculate what is called flux. Therefore flux of electron. Flux means number per unit time per unit area. This is what we call as flux. Flux of electron is number of electrons crossing the area, crossing that cross section per unit time per unit area. Okay, so that is going to be equal to NVD into A divided by A. So this A cancel and we get the flux, and therefore current, or we can say drift current density due to electrons is equal to NVED into Q. NVED into Q. That's it. If you want, you can combine N into Q and into VED. Okay. So VED is basically the drift velocity. These are subscript and superscript. So this is the drift velocity, and this is what? This is basically the charge density. N is the number density or concentration. Okay, concentration is also called as the this one is also called as number density, or number density. That means number of particles per unit volume, and this is basically charge density, coulomb per unit volume. Okay, which is usually denoted sometimes with rho, but I am not using rho here. Let's keep it like this: NQVD. Therefore that is J DRF, that is drift current due to electron, is equal to, so if I bring in Q in terms of modulus, So then I will have minus n into, let me write q first. So this is q, I can write it as minus modulus q into n, that is the concentration of electrons, which we derived in earlier classes. And then a little while ago we said this velocity is proportional to mobility. So the expression for mobility was also given. So mu e into e. Okay, where mu e is the mobility. So where I have used where v e d, I took it as mobility of electron into electric field. So this is what we have now. Usually when we say mobility, we only talk about the modulus of it, and if we are doing so, then you can absorb the minus sign in the expression for electron. So you can define, if you want to define it as a modulus only, that is also okay. So if you do this way, then this sign will be plus here. So mobility will be defined as a positive quantity, but then for electron what will happen is that if I say, so this will be written as minus q tau v by n star into e. So this is our mu e, and there is a minus sign here. Okay, so this is also a good way of looking at, and this is how I think the books it is written. So we will also follow that. So when we substitute for velocity, so we will have to say it is minus this. Okay, minus mu, and now mu e is what? Mu e, we said it is tau, and star was there, tau was there, yeah, q tau m star. So mu e is equal to modulus q tau m star. Okay, so now everything is there. So if you want, you can substitute all this for mobility. So you see that there is a minus sign here. So that minus sign after substitution will become plus. Okay. If I define my velocity as minus mu e into e, so when I substitute for the drift velocity, I will get a minus sign, and already there was a q here which I wrote it as minus modulus q. So these two minus signs, maybe I will explicitly show it in order to avoid confusion. Let me rewrite this again. So I will say n into minus modulus q, okay, that is this, and then I will say for Vd or drift velocity, I will write it as minus mu e into e. So this minus minus will cancel, so therefore it is modulus q, then n mu e into the electric field. Now this is basically the Ohm's law. We have derived the Ohm's law for by considering the motion of electrons. Now similarly we can but this is only part of the story, but we can have drift due to the holes also, considering the drift current density So let me say similarly, okay, similarly considering the drift current density due to holes, we get J, instead of electrons I have holes. Okay, yeah. I will put Jn and Jp. So Jn is for electron. I think earlier I have used somewhere I have specified Jn. Okay, let us use it as, I think in the title I have specified it as Jn. Yeah, Jn drift and Jp drift. That is the contribution from electrons and contribution from holes. So Jn drift is equal to Q. Okay, so let's now look for holes. Okay, so this will be Jp. Now if you see the detailed derivation, so we have n into minus q, n into minus q, minus modulus q here, but for the case of holes, the charge density is going to be n into modulus q. That will be the charge density. And then we have the drift velocity, and the drift velocity will not have minus sign. Okay, maybe I will write it one more step. Okay, I will write one more step. So this expression n VD into Q, or n Q V. So here it is V H D. Okay, it is the drift velocity of holes. Velocity of holes. Now drift velocity of holes is given by mu mu h or mu p into mu h into electric field. Mu h into electric field. There will not be any minus sign here, and mu is positive also, and mu h is modulus q tau h divided by m h star. Okay, so these are the definitions. Now if I substitute, so q is for holes, the charge is basically, sorry, one more thing I made mistake here is, instead of n it will be p, concentration of holes. So p, sorry, modulus q, I can write q as modulus q into p into VHD. VHD is basically mu h into e. Okay, so these are the expressions. So therefore we have derived two components for drift current, and if you add up these two drift current, we get the total drift current. So one transport mechanism we have almost derived. So therefore total drift current J DRF, if you want you can put it T, capital T here to say total, but if I don't put N or P, you assume that it is total. Jn drift plus Jp DRF. So which is equal to, so whatever is common in the two terms, let's take, there are few terms which are common, I think, or yeah, electric field is common and modulus q is common, and n mu e and P mu H. That is the difference. So we'll write it as modulus Q into N mu E plus P mu H into electric field. Okay, N mu E plus P mu H. So this is the Ohm's law in point form. So this is the expression for Ohm's law. It is J drift current density is equal to sigma into electric field. So what we get is by writing down or deriving the Ohm's law, we got the conductivity, where the conductivity sigma is given by one part coming from electron transport and the other part coming from hole transport, mu H. So this is a very important relationship. We can do problems with it. Okay, so this is the expression for conductivity, and this is Ohm's law. Okay, this is what I little while ago I said, E is equal to rho into J. We can write in this way also, where rho E, which is resistivity, is 1 by sigma conductivity. So either way you put it, this is Ohm's law. So conductivity is a material property, whereas conductance and resistance has material property plus its geometrical aspects. Okay, and we can go from one to the other, as I told you. So if you consider a cylindrical conductor or a rectangular conductor, you can go to a rectangular, okay, a cuboid. You consider a cuboid like this, then the formula that we derive, we can integrate it. Okay, so what is the current that is flowing through this semiconductor block? Okay, so this is semiconductor block. Now we apply some voltage here across it. Okay, we apply some voltage across the semiconductor, say plus minus. The length of the semiconductor, let's say it is L. Okay, so assume that this is some kind of compensated semiconductor block, which has both kind of doping, but it is uniform. Okay, everywhere it is uniform. Otherwise integration will become difficult. If n and p, if it varies with position, then the calculation will become a little more tedious. But if you assume that it is uniformly doped, and this cross section, if you say this cross section area, we will call it as A. So I, you can say, is basically J drift into A by definition. Okay, so that is number one. That's a relation between current and current density. Also, we have voltage or electric field. Electric field is what? Electric field is voltage divided by L. Okay, if you apply some voltage V, and then the electric field inside the semiconductor will be that voltage applied divided by length. Okay, so that is number 2. So if you combine these two, so then you can convert the relationship that we have, that is substitute for J therefore J drift is equal to I by A is equal to I by A, you can say it is equal to sigma E, and then you substitute for sigma E, which you can write it as sigma into E by L. Okay, so therefore what is V? V is basically L by A okay, so okay, so what we will do is we will combine, we will equate these two. Okay, so either you can write that is I is equal to A by L then sigma into V. So this is one way of writing, where conductance into voltage is equal to current. Or you can invert this and write it as V is equal to L by A into 1 by sigma into I. So this is alternatively R into I. Okay, so these are familiar forms of Ohm's law to you. We can get it very easily from the differential form which we have derived. So that's it. That's the drift current density, and if you want, you can write this as also drift. Now there is another mechanism of current which I will come into after a while. So let's have a break and we'll come back.